We're going to look at granular filtration today. What we've seen so far in the classes, we started talking about drinking water treatment focused on surface water. Within surface water, our concern was removing suspended particles that are floating in water. We looked at the reason why particles are stable in water. Particles are stable or stay in suspension because of particle stability due to surface charge, electrical double layer, zeta potential, and we also looked at how we can add a coagulant and destabilize those particles. So we looked at adding alum, the effect of alkalinity and pH on alum working as a coagulant. We looked at the same for ferric chloride, and for after coagulation, we worked on flocculation basin. We designed a flocculation basin, looked at how the flocks are formed and why flocks should stay in water, not settle out in the flocculation basin. And then we designed a settling tank where the flocks were allowed to settle to the bottom of the reactor, and then the clear supernatant flows out of the settling tank or sedimentation basin. Now the water, the discharge from the settling tank is typically expected to have a turbidity of 1 to 10 NTU. It's a range of 1 to 10 NTU, and typical value is about 2 NTU. Now US EPA drinking water standard is about 0.3 NTU in 95% of the monthly measurement, and no measurement can exceed 1 NTU. Now this condition is a general one. It depends on the water quality. In some cases where you have pretty good water quality, meaning less particles in water, with just sedimentation we can achieve this. But most often that's not the case. In general, you need a settling tank which will produce water with a turbidity in the range of 1 to 10 NTU, and then you use filtration to get US EPA drinking water standard of 0.3 NTU. Now filtration, we are going to specifically look at granular filtration. So granular filtration, now within granular filtration we have few different types. First one, a slow sand filter. Second one, a rapid sand filter. Third one, a dual media filter. And the last one, a multimedia filter. We'll look in detail on what each filter means. So these are the 4 basic types of granular filters. Dual media, as the name implies, it has 2 types of media. Example, you can have anthracite coal, plus sand, fine sand. Multimedia, 3 or more types of material. 3 or more types of media. So first one is a slow sand, which means it's a sand filter. It is called slow sand mainly because of the rate at which it can filter water. A rapid sand, there is some modification. We'll talk about what the modification is, and it's faster than slow sand. Now the dual media is supposed to be even faster than rapid sand, multimedia, more faster than dual, and more efficient. We will look at the reasons why one is faster and more efficient than the other. Before that, what are the different mechanisms of filtration? We have four different mechanisms of filtration. I'm going to turn on the overhead projector. It's going to get a little noisy now. It's a projector noise. So the mechanisms of filtration. Okay, let's give it a second. It's going to pull up the image, and then we'll talk about what the filtration is, or the mechanism is. Okay, so actually I said 4. It's going to be 5 different types. So 1, 2, 3, 4, 5. The first one is called mechanical screening. So A is mechanical screening. B, C, D, and E. So the difference between A and the other 4 types is the filtration A, it happens on the top surface, meaning this is a particle, an example particle in water. Okay, that particle is too big to pass through the filter. Now these are the filter granules. Or the media. So for example, let's assume this is sand. So this is sand that is inside the filter. Now we are pumping water. This arrow indicates water is flowing through this. Water flowing through the filter, and this is the particle that is present in water. Now if the size of that particular particle is too big to pass through the small pores or spaces in between the sand granules, so it is stopped at the top, and more particles get stopped at the top, and clean water flows through the filter. Now as the particles get stopped, sometimes there is a biological layer or a biofilm forming on top that makes it even more efficient. But since it's mostly on the top, this process doesn't include the deeper portion of the filter. The filtration is concentrated on the top, so eventually it becomes slow down. And it can't take advantage of the whole filter. That is the kind of process happening in slow sand filter. So this is a mechanical straining where you have the filter, water flows through, particles and water start getting trapped on the surface, and it gets built up on top of it, and the buildup goes on for a while, and at some point you can't pump enough water through it. In other words, it gets clogged. So you stop, remove waters on the surface, and then again start using it. So that is the first one. Now B, this one right here, is part of in-depth filtration. So in case of B, it is called sedimentation. C right here is flocculation. D is called interception. And the last one is called impaction. So what happens is, in the case of B, the particle is right here. So this is the water flowing, water, and right here is the particle. Okay? Now, this particular particle are small enough compared to this one. The particle right here and here are small enough to pass through the pore spaces, but they are too big to flow all the way through the filter. Instead, they settle on the filter granules right here. So this particle right here is going to settle right on this granule, and this particle is going to flow and settle right here. So that is called sedimentation, where particles are small enough to pass through the filter granules, but at some point it kind of settles on one or more granules. That is called granules, meaning the filter material. In this case is sand, fine sand. So that is sedimentation. You see is flocculation. Now again, you see the particles. They are small enough, they can flow through. Now as the water flows through the pore spaces or the space in between the granules, two or more particles join together, meaning they flock. When they form a flock, they become bigger, and then they can pass through this granule. It kind of gets filtered at this point. So this is called flocculation, filtration by flocculation. Now the third one, which is interception, again you have the particle right here. Now the granules or the material that forms the filter, in this case a fine sand, the surface of the sand is not smooth. You have ups and downs or cracks. So some smaller particles, that are tiny particles, they get trapped or intercepted at the irregular surface of the filter granules. So it's interception where flowing particles, if this is a granule, particle flows through and there is a irregular shape and the particle gets attached to the granule on the surface or on the side, because it has kind of a curvature where particle is too small, falls there and stays there. That is called interception. Now the last one right here, which is called impaction, is similar to sedimentation, but it's just that the particles are kind of small, they can travel, but they're heavy to the extent where they can't travel as fast as water. So they flow through water to some extent, and then they kind of hit the filter granules and get trapped there. So these are the 4 different types of in-depth filtration mechanism, meaning the filtration happens inside the filter, takes advantage of the whole depth of the filter, whereas the mechanical straining is surface process, which happens only at the top. I'm going to turn this off now. It's going to get a little quieter in a minute. All right, it's quiet now. Hopefully you can hear me better. So we looked at 5 different types of how particles can settle inside a filter. Now what I want to do is talk about the difference between the types of filters that we saw earlier. So we looked at, or we started at slow sand filter, and then a rapid sand, and then a dual media filter, or 2 types of media. Okay. So slow sand, the flow rate, slow sand, as the name implies, it's a filter made up of sand material. The effective pore size in a slow sand is about 0.2 millimeters. So that is the spacing in between the sand particles inside a filter. So whatever particle we are trying to remove, they have to get trapped within this pore space. Flow rate equals 3 to 8 meter square per day or meter cube per day per meter square. That's the flow rate. Slow sand requires large area, more labor. Initial capital cost is less. Initial cost is less. Now, rapid sand is the effective pore size is 0.45 to 0.55. Rapid sand has graded layers, meaning a top layer smaller pore size, bottom layer bigger pore size. Typically, the smaller pore size is due to fine sand. Larger pore size is coarse sand. And they have a higher flow rate compared to slow sand filters. The flow rate is 120 meter cube per day per meter square. So now what happened is, between slow sand and rapid sand, slow sand has uniform material all through the filter, which is fine sand, and it has one type of pore size, and so which is about 0.2 millimeter. And the major mechanism in a slow sand filter is mechanical straining, meaning it's a surface process, and it is slow. Because of that, it is slow, and it can only treat about 3 to 8 meter cube per day per meter square. Because it can treat only small volume of water, it needs a large area, more labor, but it initially costs less. Now, as the water demand increased, we needed a faster process. So we came up with a rapid sand. Now, rapid sand, the effective pore size. Effective pore size, meaning it has two types of layer, a top layer and a bottom layer. Top layer made of fine sand, bottom layer coarse sand. The combined pore size is about 0.45 to 0.55, which allows faster treatment of water. So that helps. But again, the problem is, since you have fine sand in the top, meaning you have smaller pore openings or smaller spaces between the fine sand, whereas the coarse layer at the bottom has bigger size opening. So when the opening is bigger, you can allow water to pass through faster. But even before we take advantage of the bottom layer, the top layer can get clogged because it is smaller in opening, so particles are trapped in the fine sand layer and eventually it gets clogged. And if the fine sand layer is clogged, water cannot pass through this one and get to the coarse sand layer. So it is more efficient than the slow sand, but still we have the problem of top layer clogging faster than the bottom coarse layer. Now, how do we fix that one? One way to do is if we can reverse it, meaning if we can have a coarse layer at the top and a fine layer at the bottom. If we have that, coarse layer will have bigger pore spaces, so water can flow through it faster and only bigger particles get trapped at the top. Smaller particles can pass through those particles along with water, and when they reach the bottom layer, if you have a fine sand, they can be removed in the fine sand layer. Now with sand, we cannot do that because coarse sand is going to be more denser than fine sand. So once you arrange it, start pumping water, the sand layer will automatically rearrange and force the fine sand to go to the top and coarse sand to flow to the bottom. So that is not possible, meaning having a bigger size at the top and smaller size at the bottom is not possible with just the sand. That's where dual media or two types of media came into play. So for two types of media, we need a material that is bigger in size but has a density that is lower than sand. So if we can find a material which is bigger than sand but not as dense as sand, we can put that on the top. That will allow smaller particles and water to pass through and trap the bigger particles. Now as it flows through, the smaller particles can be trapped in the bottom fine sand layer. So that is the idea of dual media filter. I'm going to take a break now, get you a few more slides set up, and then we'll continue.